ready? Conservation of momentum, conservation of momentum. I can break this, I can break this. And, oh, hey everybody. Go, shoot. All right. Hi everybody. Welcome to another walkthrough video with Physics with Dr. T. I'm Dr. T, and this week we're taking a look at collisions, conservation of momentum, and what happens during a collision, all the stuff that happens between constant velocity, constant acceleration. Before we dive into the details on that though, let's take a look at this week's pre-lab activity. So in order to dive into the theory on this, it's important to think about where we're coming from. Up until now, we've looked at motion, we've looked at causes of changes in motion, which would be Newton's laws of motion. In particular, Newton's first law that says don't mess with it and either watch it sit still or continue at a constant speed. Or Newton's second law that said let's irritate it, let's bother it, let's put a force on it and watch it accelerate. We kind of neglected the third option. We kind of dealt with it a little bit when we came up with this thing called a normal force. But there's another application of Newton's third law that's a little bit more potent, if you will, in the situation, because Newton's third law talks about two objects that are interacting with each other, where the action on one results in an interaction that comes back in the same amount. So remember what Newton's third law says. Newton's third law says for every action there's an equal and opposite reaction. Or what I like to think, what about the other guy? What happened to that when that was applying a force to me? And so we indicate that equationally, the force acting on the second object is equal to the negative of the force acting on the first object caused by the second object. For example, a common thing you might think about it would be like swinging a baseball bat. We think about the baseball primarily for Newton's first and second law. Then Newton's third law comes in, and it's the bat colliding with the baseball during the swing that this kicks in. So let's break that down and see where it goes with this. So how do we apply Newton's third law to the situation of a collision? Here we have two objects that we expect to collide. And let's say one's at rest, the other object comes in and comes into contact. During the contact, this ball is now applying a force on this ball, but because this is at rest and it's resisting the change, it's going to push back on this ball and create a force going in the opposite direction, equal and opposite. And we have that written up here in the form of the force by mass 2 acting on mass 1 is equal to the negative of force by mass 1 acting on mass 2. A couple of characteristics to keep in mind about this. Number one, the point of contact does not move. Once they are in the middle of a collision, there's no movement. If there is movement, it changes the situation a little bit because chances are you're looking at deformation. The object is no longer the same shape it was before and something could be happening there. Or it could be completely shattering and coming apart, which means it's no longer actually transferring the same amount of force from one object to the other. So we're going to assume that the point of contact does not change in position, doesn't accelerate. The other characteristic that comes of this is that the contact lasts the same amount for both of the objects. That means that we can multiply this equation by the same delta t. Time acts on these the same period of time, and so now we have an expression that says force times displacement in time. What happens when these two objects collide with each other during this time frame where there's a force acting over a period of time? Well, one of them is going to win the collision, such as one wins a collision. The one of them is going to win the collision and cause the other one to change direction of its motion. And up until now, we've covered just about every observable characteristic about motion. The actual position of displacement, we talked about the force it's acting on, we talked about the energy it could have. One other thing, where you have the mass and its actual speed. We refer to that as momentum. P equals mv. Why do we use? Because everybody knows momentum starts with a P. But this is the variable that we use now, with the letter m representing the mass, and v, the velocity or the speed of the object. Momentum in this case is a vector quantity, and we can define the force acting over that period of time as corresponding to the change in momentum that happens on that. We refer to that as the impulse. Substituting this definition into here, then we can define that the change in momentum of mass 1 corresponds to a negative of change in momentum of mass 2. So whatever momentum changes for mass 1, whatever its mass is probably not going to change. We're going to assume the masses don't change in these situations. So whatever its velocity qualities are, remember velocity is a vector, so it's not just magnitude, it's direction as well. Whatever changes about the velocity quality, and thus the momentum of mass 1, it's going to have an impact and be equally balanced by whatever the mass difference of the two is, leading to a change in the velocities of mass 2. Shifting these all into one side, we get a first definition for conservation of momentum, which is that the change in momentum for mass 1 and change in momentum for mass 2 should cancel each other out. We get 0, and you will be testing these in the course of your lab in this week. Of course, we can rearrange these quantities in such a way. We break them down into final minus initial, rearrange them so we have all the initial on one side, all the final on one side. Notice that everything comes out negative in the way that I rearranged it in this case. So divide by -1, and we say the sum of all the momentum, or of every particle that's involved in this system of interest before whatever the collision is equal to the sum of those momenta for all those masses and particles after the fact. This statement is our second condition of comparison. We're going to compare these two before and afters in the course of our experiment. And we can rearrange it in such a way, and we got our second, or version 2, if you will, of conservation of momentum, which states that the total momentum beforehand minus the total momentum afterward should equal 0. In other words, there's again no change in momentum in the course of an experiment. So where does that take us? It means that there are different types of collisions that will have an effect on momentum. It means that we have different ways of checking our momentum in the course of our experiment. Now, there could be different types of collisions. Let's consider what types of collisions we have. Notice that there's no conditions on anything here about what's actually happening during the collision, only what the states are right before and right after the collision takes place. So in all types of collisions, momentum is going to be conserved. But is everything conserved in the course of that collision? The answer is going to be not necessarily. Here we have a type 1 of collision, a very simple collision. This is your billiard ball collision. The cue ball hits the 8-ball corner pocket, whatever. The momentum is conserved when those cue balls clack into each other. Energy is also conserved. We refer to that as an elastic collision. Type 2, which I've got as a 2A, momentum is conserved still, however, energy is not conserved. Why? Because energy is lost to some factor, and so energy is not conserved, and notably, the objects will remain separate in the course of that experience or that interaction, and that means we refer to that as an inelastic collision. Finally, there's type 2b, which is momentum again conserved, energy still not conserved. The objects in this case stick together. Think of a car accident where they wrap around each other and have to be tugged apart in order to be able to be towed away, or some such similar situation. In that case, we refer to that as perfectly inelastic. That covers everything. Let's do the experiment. Fun fact, if you stick around to watch this part, I will tell you. Linguistically, elastic just means that you apply a force and then you take the force away and it returns back to its original state. Rubber bands are elastic. But plastic are, I like to say pelastic, because they are, you apply a force and then they deform, and when you take the force away, they stay in that place. So you bend plastic, it's not elastic, it's plastic. So anything that's plastic will change, like putty would be an example. So just a little fun linguistic sided note for you language nerds out there. All right. In this week's lab, we'll be working with two carts, one red, one blue. This is to help you keep track of which one is which. These are smart carts because they have all kinds of gadgets and gizmos built into them, including an ability to measure its position, speed, and acceleration at any location throughout its run, largely to do with the motion of its wheels. And it's got a few other abilities, such as sensing the force that's acting on it and other tools that we won't be using. It's got one side that's got magnets that are indicated with these little magnetic, look like magnetic loop symbols. And then the other side that has Velcro or hook and loop that are make it easy for these two to connect to each other. A little bit of familiarity of what you're looking at here. This is a Bluetooth connection that's going to connect to the device. We'll see that in a little more detail in a moment. And then you have a battery indicator. It will look red, but they should be pretty well charged by the time you get to working with them. And to turn this on, make it ready to be seen by your device, you simply power it on, watch the red light come on, and then it'll start flashing regularly, gently while it's trying to find your Bluetooth signal. Once you're done working with these, you do want to reconnect them to the power source so they can charge up throughout the in between lab activities. An additional feature of these is a trigger that allows you to be able to set up the explosion step in one of your collisions. And they are designed to be able to hold either the full size mass that has a certain weight or a half-size mass, which will be beneficial if we tape that down somehow and make sure that it's held fast in the collisions. Once you have your masses of your carts and the blocks, you can set them onto the track. Make sure that they sit well into the grooves and are moving smoothly. If they're offset a little bit, they're not going to have as much efficiency in their going. You have collisions where the magnets are repelling each other. You don't want them to go so fast that they actually clack. That's a loss of energy. You want them to just collide with each other magnetically and not lose energy in the process. You can also flip them around, have them capture each other using the Velcro in that case. So once we get into the CAPSTONE software, the first thing that we want to do is go ahead and connect with the carts. So we come over here to the hardware setup as usual. The 850, whether it's turned on or not, is going to be irrelevant in this case because these devices are connecting through a Bluetooth dongle that's connected to the device. So what you're going to look for in this case is, I'm going to turn this back on because they went to sleep. And you can see they show up. So you click on one. There may be more than just this one or two here for each color because you're local areas. So just click on the one that matches the 6-digit number that's on your cart. Give it a few moments to try and figure itself out. And then it connects. I'd go and turn off the gyro sensor. Probably not going to use the acceleration sensor, but we'll leave that on and then start the smart cart. All right, so turn off the smart gyro. We'll go ahead and click over to data summary because as usual we want decimal places. And we'll do, so turn the velocity of the blue cart, turn that to 6 decimal places, 7 actually because we have 3 defaults, so we'll give it as many. Maybe not use it, we're not sure, but in particular we're going to give it a try since time has 3 defaults, then we can go up to 7. So we're going to assume a same pattern in this case. Go to time. We only need the speeds and the time because that's what we're really going to be looking at. But also the force. So let's turn that on. Give ourselves as many decimal places to work with that one. That starts with 2, so we'll go up to 6. Click OK. So we're just trying to give ourselves extra decimal places to work with. Format. Click OK. And we close that. Now, before we continue into getting data, we need to reset the force sensors before we make our measurements. So you're going to need to do this before each run so that your force information is best. As you can see in this graph, the 0 value, when it was not, there was no force acting on them, they were just either at rest or in motion, that the net force was still showing as non-zero here in the background. So we've got to fix that. To do that, we go to the Smart Cart force sensor, click on the gear. You're going to see in the pop-up a 0 sensor now. You just click on that. Just click on that and then click OK. Go down, make sure you do the same thing for both. 0 sensor now, click OK, and then you can close this. Bring a graph onto top half, and I'm going to turn this to velocity blue, but we also need to have the red showing simultaneously. So we're going to click on this and add similar measurement, add red, and now you notice that the axis has been relabeled to just velocity, not just velocity blue, and the automatic setting for time on the horizontal. I'm going to grab a second graph and bring that out and put that down at the bottom. I'm going to make that one the force blue, and then again click on this and add similar measurement, force red. So now I'll change the vertical axis to just force, and we need to set the sample rate high enough so that we get useful data out of this. If we go a little too high, we're going to see too much nuance in the motion, such as vibration and so forth. So we want to avoid that. In this case, I'm going to set these in this video to 150. By the time you watch this and you're working on this in the lab, I may have changed that value to a more suitable value. So start with 150 hertz down here, red position sensor. We're going to boost that up to, let's see, I guess 200 hertz is fine. 100 cycles per second, that should be actually okay. 100 cycles, 100 hertz. We're going to start with 100 hertz. Then I'll change this to the position blue. Let's say 100 hertz, right? And then for the force sensor for these, I'm going to boost those up to 200 because of the narrow period of time. We need more samples in that to have a smooth curve. So we're going to boost the forces up to 200 cycles per samples per second. And now we're ready to take data. Okay, so now we've taken the data, and the next step is taking the data, interpreting the data as usual, and then putting it into some kind of interpretable format. So let's take a quick moment and look at the spreadsheet that you have available. Now, it could be something that you can calculate for yourself, but there's a lot of calculations in this, and I want you to focus on the science and interpreting the results more than I'm worried about you getting into Excel and putting calculations in or doing the calculations on your phone. This is simply calculations of momentum and energy, and so it's I think a little bit better idea to focus on understanding the tools that are available to you and using that to help guide your understanding of the physics that we're taking a look at. So here I've got this version of the spreadsheet, and what I've done this year is modified this spreadsheet so that each collision has its actual own tab at the bottom, as you can see, and then you can go into each one of them and enter in information. Now there's a lot going on these sheets, and I can make them black and white, and you're welcome to change the colors for your own satisfaction, but I've tried to color code them to help guide your understanding of what's going on there. So on the first page is just the data input. So this is the masses of the carts, and feels like I should put more there, but I decided against it. I thought I would just be enter your masses of each object in this field in grams as measured directly on the scale, and then it's converted immediately into kilograms, and then that information is fed automatically to other pages where it's just sitting up there to be used. And in this case, you can see that I've put in a formula that says, okay, the red cart in the videos you saw is the mass of the cart plus a block that we had sitting on there. So I have the mass of the block added together in the formula you see here. Escape always takes you out of what you're doing. And then the mass of the blue cart is pointing to the blue cart's mass in kilograms. Everything's in kilograms. So all we need to enter in here is knowing what all we need to enter in this field is the initial velocity. So all we need to enter now into these four fields is the initial motion and the final motion of the both carts. So that takes us to analyzing our data. So let's jump over into this and taking a look. You can see that this is the data that we just ran, and there's some stuff going on. You can clearly tell which one is red and which one's blue cart, and that's a nice feature of this process. But the question is, what are we looking at? Again, we always want to be able to look at data and understand what we're looking at. So notice that the top graph is velocity versus time, which means that we're seeing speed increase and then slow down some, probably under friction, and then this sudden shift that both carts share around the same period of time. And then you've got continued motion after the fact, and then some other business happening here. If you're not clear about what's going on when you're looking at the data, part of the reason that we're looking at the force data is to kind of help that along. You'll notice that the force doesn't really have anything happening except for a little bulge here due to when you give the blue cart a nudge. In this case, in my case, you can do swap those options of out and as you like. It is just a way to go, and I encourage you to try doing a different way to stretch that analytical leg of yours. So we come over here and you notice that this big spike here is where they're actually colliding. And how do we know that that's the case? Well, it's a good guess, I think, because there's no other forces acting except for when we push it and when they collide. And pushing it is an act on one, colliding is an act that takes both of those involved. This is the only force data that shows both of them having simultaneous action. So that means that corresponds to this ramping right here of the data. So we're going to zoom in on that for both of those. So we grab this, drag it down to the left, and then grab the axis and stretch it out so we can see both the before and after pretty well. And we're going to go ahead and grab the force information and do the same thing about that as well. It probably doesn't need to go quite as far. And stretch that out. We can play with it until we get what we're looking for. Stretch it out, stretch it out. And it might even feel better to just kind of set it right around the same space as the other one. We could even stretch that just a little bit so that they have the same-ish size axes. There we go. Okay, so what is the initial velocity of the carts? Well, the red cart should be 0, so I'll go ahead and enter that in this case because the red cart was at rest. And then, so one thing that will be helpful is to go ahead and throw an active space over the initial data and then stretch that out. Now, there is some, if we zoom in on this, you can see that there's some action in the beginning that is entirely unclear about what's going on here for this first bump, but there's definitely some kind of interaction that's taking place in this spot. So let's move this back down, and that's not what we're going to use for our reference for when it stops being 0 just yet. We're going to look at the blue. So activate the blue line by clicking on it, adding a trend. Let's zoom that down. Let's bring that down just a little bit more. And we'll just adjust this, make sure we have a good trend of data. And I've added a linear fit here. And what we're looking for is basically where the first data point that seems to break away from the trend is. And I'm not zoomed in here, but you'll have the opportunity in person to zoom in. And what I'll do is I'm going to click on a data point and add a flag there and move that to the last data point that appears to still be in line, which I want to say is actually right here. So that's at time 10.35 seconds, and I'll add one similarly to the red. And I'll enter those values in. Now we have to be careful about something. Remember that these carts have a preset axis, so we have to keep in mind that one direction is moving positive. We have to keep in mind that for one of the carts, its motion is positive in the direction of its positive axis, whereas the other one is negative relative to that same axis. So we have to pick an axis, say left, right, or whatever is the positive thing. So my general characteristic is anything to the right is positive, anything towards the left would be negative. So when the blue card initial motion is going, when I push it from right to left, and in doing so I gave it a negative motion relative to me, not relative to you but relative to me. So I'm going to put it in as a negative initial velocity, and the red cart continued moving in that way, so its final motion is going to be negative, and we'll take a look at that in more detail. So here I see that my initial speed for the cart is negative 0.004. I want that to stay 0 because I want to assume that we're close to 0. That may be a not good point because of that little bit of stuff. We'll see when we look at the percent error. And then I'll put the value blue over here, and that one is going to be initial negative 0.5658905. Nope, there's an extra 0 in there. So let me turn that off. And then, and you see that you can put all the decimal places in there, but I've truncated the decimal places for clarity. And then for the red, we'll do the same thing. We're going to grab this and move this to another point, add a trend line of linear fit because the behavior is linear. And I'll try and align those using the same range of data. And I'll look for again, where the fit stops seeming to represent. So I'll go to the data point, the last data point that seems to fit in there. And let's move this out of the way just a little bit so we have more space. Zoom this over here to right around this guy. It looks like that's the last one to me. Negative 0.10 or 10.51 seconds. So I'll move this because we're going to assume that the two are giving simultaneous data. Now remember, this is negative, and looking at the cart's motion, the blue cart bounced back and went the opposite direction. So now it's moving positive. This is saying negative. So we're going to write that in here as a positive 0.1697672. And for the red, looks like they're at the same timestamp. This is going to be actually going negative, so we can record the value as it is, negative 0.3880392, a bunch of decimal places. Center line, okay, and then. And now we've entered those 4 values in, it's time to look at the results. You can see that when we look at the momentum analysis, if we're comparing the sums, the before and after sum of total momentum before and total momentum after, we're in very good agreement. As far as the change in momentum for each cart, also very good agreement. We've got negative 0.52 for the sums and positive 0.40 for the changes. How does the energy compare? This is going to be our prediction because up at the beginning we say, oh, I predict this is going to be a elastic collision because it's just going to be them bouncing off and the magnetic field doing the job. And we can see that it punches the values in, and the total of the sum of kinetic energy before and after seems to be in agreement, and the changes are after, and the changes comparison also in good agreement, well, good agreement. Therefore, the momentum is conserved, and the energy is conserved, yes. And we scroll down just a little bit further. We're going to check out this impulse during the collision. One more way to check and see if everything went well. So what we're looking for with collision is, for impulse, it's the force times time displacement, or force times the duration of the collision. And that's going to be the impulse, how much went into changing momentum. And we do that by getting the area of the force versus the time value. So we'll come back over to the graph, and we see that the red Here, remember, if you did not zero the sensor beforehand, this is going to be offset and give you a wrong value of area because it's going to subtract the negative and the positive are going to cancel each other out in such a way that it reduces the actual net area that's counting for your active spots. So we turn on the area there, and immediately it looks like it's going to be something, but let's get we come in and we say, okay, the time of collision seems to go, I think we said it was like 10.35 to about 10.51. So we make sure that we have that same, and always make sure that you include the entire area. And now, during the time of the collision, during the entirety of the collision, the duration, the net force overall during that time is going to be, well, not the net force, but that's going to be, we're going to use the positive value, the absolute value, 195,938, and that's in good agreement. And then we can move this out of the way and activate the blue, turn on its, make sure you're careful now. We're not going to use the red information for the blue cart. So about 10.35-ish. And turn the area on under that one. And this one's 0.18355. Enter. That's a little bit higher. And now you can begin to analyze what do you think is going on in there that could be contributing to that little area. I'm going to tell you the answer to this one is look at the nature of that curve right there. Look at the nature of the curve. Look at other things that you might see in the nuances of here. Doesn't have to be a great deep analysis. You've got good momentum agreement. You've got good kinetic energy agreement. And now it's just a matter of going ahead, resetting your system, and going to your second collision and beginning and continuing from there. When you're finished, one of the worksheets is going to be a printable for report, and that's going to allow you to print the net results from these collisions out onto a piece of paper for you. You'll need to write your summary, and you'll also need to export your data for one of your runs from CAPSTONE, get it into Excel, and then just print the relevant range for your lab report. And that's it. Well, that does it for another walkthrough. If you have any questions, feel free to talk to me, talk to your TA, talk to your lab mates. Sometimes the best way to learn stuff is by talking with your classmates because they're speaking your language a little bit better. So until next time, we'll see you in the lab. All right, let's do this. All right. All right, next we need to shut down, move down. We got to Mad Hatter this out. Train of thought. Through a Bluetooth dongle that's connected. What a ridiculous word, dongle. It's a dumb name for technology. So let's see here. Stand, blah, 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 blah. Let's talk about this. All right. So, shut you, quiet you. That's good stuff. I was like a little game, right? All right, so we're going to talk about collisions, and I'll be like, well, before we get into that, let's talk about this week's periodic activity. Okay. Or even if one's about rest and one comes in. I was as sloppy as everything. I'm going to appear like this. Googly eyes. Maybe. All right. So let's take a quick moment and talk about not scratching my head while I'm working. Okay. That microphone's going to go right here. Hello. Hello. All right. How do you trim these things down from 1 hour and 20 minutes down to a 17-minute video? It's pretty entertaining. Okay, so. And so we indicate that equationally as, yes, I just made up the word equationally. Circled by the ring of fire is Newton's first law. Second law. All right, train of thought. So, all right, blah, 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 words.